Learning and optimization, two concepts often intertwined, represent distinct processes with profound implications. While both utilize gradients for guidance, their objectives and domains differ significantly. Understanding these differences is crucial for comprehending how systems adapt, evolve, and solve problems. Imagine a child learning to ride a bicycle. Through trial and error, they adjust their balance and movements, gradually improving their stability and control. This embodies learning, a process of acquiring knowledge and skills through experience. Now, consider an engineer optimizing a car engine for fuel efficiency. By tweaking parameters like fuel injection timing and air intake volume, they seek the optimal configuration that minimizes fuel consumption. This exemplifies optimization, a targeted search for the best solution within a defined parameter space. Although both scenarios involve iterative adjustments based on feedback, they operate on different levels. Learning focuses on acquiring generalizable knowledge from interactions, while optimization aims to fine-tune existing systems for specific outcomes. Recognizing this distinction is paramount for understanding the dynamics of complex systems. At the heart of both learning and optimization lies the concept of gradient following. Imagine a hiker navigating a mountainous terrain, seeking the highest peak. With each step, they assess the slope, choosing the direction of steepest ascent. This intuitive strategy exemplifies gradient following, a process of iteratively moving towards a desired outcome by following the direction of greatest change. In mathematical terms, the gradient represents the direction of steepest ascent for a given function. By calculating the gradient at each point, we can determine the direction that maximizes or minimizes the function's value. This principle underpins numerous algorithms in machine learning, optimization, and control systems. For instance, in training a neural network, the gradient of the loss function guides the adjustment of network weights, gradually improving its accuracy. Similarly, in optimizing a manufacturing process, the gradient of a cost function directs the modification of process parameters to minimize production expenses. Gradient following, therefore, serves as a universal language for both learning and optimization, enabling systems to navigate complex landscapes and achieve desired outcomes. While both learning and optimization employ gradient following, they differ fundamentally in the variables they manipulate. Learning primarily deals with internal variables representing the system's internal state and knowledge representation. These variables are often hidden and abstract, reflecting the system's understanding of the environment. Consider a language model learning to translate between languages. Its internal variables encompass its grammatical rules, vocabulary, and understanding of linguistic nuances. These variables are not directly observable but are inferred from the model's performance on translation tasks. Optimization, conversely, focuses on external variables representing the system's controllable parameters or settings. These variables are directly adjustable and influence the system's behavior in a predictable manner. For example, in optimizing a robot's movement, external variables include joint angles, motor speeds, and trajectory parameters. Adjusting these variables directly impacts the robot's motion and allows for fine-tuning its performance. This distinction between internal and external variables highlights the fundamental difference between learning and optimization. Learning seeks to adapt the system's internal representation of the world, while optimization aims to find the optimal configuration of its external parameters. Section 4. The Swan Song, Induction and Generalization in Learning. One of the hallmarks of learning is its ability to generalize beyond the data it was trained on. This capacity for induction, drawing general conclusions from specific observations, lies at the heart of human and artificial intelligence. Consider the classic example of all swans are white. Having observed numerous white swans, one might induce that all swans are indeed white. However, this conclusion, while reasonable based on the available data, is readily disproven by the existence of black swans. This illustrates the inductive nature of learning. Systems learn from limited data, forming generalizations that, while useful, may not always hold true in all cases. This ability to generalize, however, is crucial for adapting to novel situations and making predictions about unseen data. Optimization, in contrast, does not inherently possess this inductive capacity. It focuses on finding the best solution within the specific data and parameters provided without necessarily generalizing beyond this scope. Section 5. Finding the needle in the haystack. Optimization's quest for specificity. Optimization, unlike learning, strives for specificity. It seeks the optimal solution within a defined parameter space, often represented as a landscape of possible solutions. This landscape, characterized by peaks and valleys, reflects the performance of different parameter combinations. Imagine searching for the lowest point in a vast, undulating desert. Each point on the map represents a specific parameter configuration, and its elevation corresponds to the objective function's value. The lower, the better. Optimization algorithms navigate this landscape, seeking the global minimum, the lowest point representing the best solution. This search for the optimal solution often involves navigating complex, high-dimensional spaces with numerous local minima valleys that appear optimal locally but are not the global best. Optimization algorithms employ various strategies to escape these local traps and converge towards the true global minimum. Unlike learning, which embraces uncertainty and generalization, optimization aims for precision and specificity, meticulously seeking the best possible solution within the given constraints. Section 6. Landscapes of learning and optimization, visualizing the differences. The concepts of learning and optimization can be further elucidated by visualizing their respective landscapes. Imagine a mountainous terrain representing a problem space. In learning, the landscape itself is dynamic, evolving as the system acquires knowledge and adapts its internal representations. Picture a hiker exploring an uncharted forest, gradually mapping the terrain and discovering new paths. This exploration mirrors the learning process, where the system continuously refines its understanding of the environment and adjusts its internal model accordingly. Optimization, conversely, operates on a static landscape. The terrain remains fixed, representing the problem's inherent structure and constraints. The optimization algorithm's task is to efficiently navigate this landscape, seeking the optimal solution represented by the lowest point. This visualization highlights the fundamental difference in perspective between learning and optimization. Learning focuses on adapting to and shaping the landscape itself, while optimization concentrates on finding the best solution within a predefined terrain. Section 7. 2 paths diverge. The implications of learning versus optimization. Understanding the distinction between learning and optimization is crucial for comprehending the behavior of complex systems, both natural and artificial. Learning, with its emphasis on generalization and adaptation, underpins cognitive processes, allowing organisms to thrive in dynamic environments. Optimization, on the other hand, plays a vital role in engineering, economics, and other fields where finding the best solution within given constraints is paramount. From designing efficient algorithms to optimizing supply chains, optimization techniques drive efficiency and performance. Recognizing these distinct approaches is essential for developing robust and adaptable systems. While optimization excels in static environments, learning proves invaluable in dynamic settings where adaptability and generalization are paramount. By appreciating the nuances of learning versus optimization, we gain a deeper understanding of how systems adapt, evolve, and solve problems, paving the way for advancements in artificial intelligence, engineering, and beyond.